Hello everyone. Here is one more example of KCL, Kirchhoff currents law. In this example, we will go ahead and solve a real circuit. So here's a real circuit that actually includes a 10 volt independent voltage source right here, a 0.5 IR dependent current source, and in fact IR is the current that you see right here. In other words, is the current that flows downwards through the resistor R. And of course the resistor R shown right here, which is 20 ohms. So the question in this circuit is to find the current I. The current I is shown right here and is the unknown current that flows outwards of the 10 volt voltage source. So the first thing I would like to remind you is that when you have an ideal voltage source, you really have no way of immediately determining the amount of current that flows out of that source. As we have learned, and you can go ahead and watch again the video for the sources, ideal voltage sources can basically give you any current you like. It really depends what you have connected to them. Similarly, ideal current sources can give you any voltage across them you like. Again, it depends what circuit you have connected. So there is no, in other words, immediate and direct equation I can apply to find the current I due to the source itself. So that means I have to go ahead and link this current to something else. If this was a current flowing through a resistor and we knew the voltage drop across that resistor, then perhaps we could have found current I by applying Ohm's law. But by doing a quick inspection in that circuit, that doesn't seem to be the case. So that plan is really out of the window. But there is another plan. Another plan could be that this current may be flowing into the node or out of a node, and I could apply KCL on that node, and if I knew every other current, perhaps I could find the current I. Indeed, this is a scenario here. If you look at this current I, it actually flows into this red node that you will see here, and this is an essential node. I have 3 branches coming out of that node. Let's see, can we find the other currents? Well, there is this outward current IR, which actually flows outwards, and then there is this current 0.5 IR that also flows downwards. Both of these currents are actually flowing outside of this node. Now, the good thing is that IR is a current that flows through a resistor, and we can apply Ohm's law to find exactly what this IR is. Why? Because this V, the voltage drop across the resistor, is the voltage drop between this red node here and this bottom node. And these are exactly the same electrical nodes as this one and this one. Therefore, V that you see is nothing else but 10 volts. So since I know that I have 10 volts across my resistor R, I can use Ohm's law to find the current. Specifically, I can write that IR, which is the current, should be equal to 10 volts, the voltage drop across the resistor, over the resistor itself, which is 20 ohms, or of course this is equal to 0.5 amps. And since now I do know my current IR, I can just as well go ahead and find the current of the dependent current source, which is 0.5 IR. So 0.5 IR, which of course will be equal to 0.25. So now I have the 2 outward flowing currents from the essential node, and so I can go ahead and apply KCL to find I. Once again, I urge you to go ahead and apply KCL consistently every time, which says that the total amount of current that flows out of that node must be equal to 0. So I will have negative I, because I is flowing into the node, and therefore negative I flows out of it. So negative I plus IR plus 0.5 IR must be equal to 0. Or I is nothing else but 1.5 IR or 0.75 amps. And that's the answer that we have. So once again, the strategy we followed to solve the circuit was by applying KCL at the essential node. There is actually only one essential node in that circuit, and try to make sure that every other current from that essential node was known. So thank you for watching this video. We will see you next time.